Yeah, thank you. And it's great being here. I know some of you might not be used to a live speaker, so just think of me as Zoom with a holographic screen feature. And if you give me a premium, I can even do no aerosolized particles. So you don't even need to sit that far away. Yeah, it's great to be here to do work that I've been doing with a lot of members of the IAS and in Princeton. This is work that entails inputting phenomenologically motivated emission models into simulations or semianalytic models with an eye for movies and polarization maps, including the one that you see behind me if you're on Zoom. On the chalkboard, you just see just see black, but you know, there are two of me apparently in the Zoom. So just pay attention to the one with the background of the Event Horizon Telescope's latest image of M87. This is the nearest horizon image that we have of M87. And I'm going to be describing a methodology that I've been using to tie the recent observations that we've been seeing to the underlying plasma physics that goes with it. So on the Zoom, it should be advanced. Let me see, there should be a movie playing. And so, okay, so when I talk about near horizon, hold on, let me just make sure that there's a movie playing. Yeah, it's good. Okay. All right. So when I say near horizon, so here's a preview of where we're headed. The constellation Virgo is at 12 hours right ascension and 13 degrees declination, and it houses our best studied cluster of galaxies. About 2,000 times the distance from here to the Galactic Center is the black hole, the second largest angular width on the sky. And the Virgo cluster galaxy that houses this black hole is Messier 87, or M87, which Heber Curtis in 1918 called the Curious Straight Ray due to that jet that you see. That extends about 100 kilolight year in radio, but we've actually imaged it all the way down beyond 43 gigahertz, scales down to 230 gigahertz into this polarized emitting ring. And this Event Horizon Telescope observation is going to be the basis for some of the models that we're going to see soon. But first, let me give you a roadmap of the talk. We're going to start with an introduction to a methodology I call observing jet, accretion flow, black hole, or JAB systems. And of course, if you're going to survive in the world of GRMD and all the wonderful work that the simulators are doing, then you have an acronym. So just give me JAB right now. Someone might make a hook simulation or a cross or something, but the first application is going to be M87, which we first observe using simulations and comparing them with very long baseline array 43 gigahertz observations and polarized EHT 230 gigahertz observations. Then we're going to observe a Semianalytic model of M87, starting with a parameter scan of Stokes maps, but we actually can incorporate effects like positrons in a very, very inexpensive way if we observe a Semianalytic model. We then have our next application, which is Sagittarius A star, which of course people are anxiously awaiting, but there are already things that without directly seeing an EHT image, we can start to infer about it using observing JAB simulations. We're going to be comparing some simulated images with some basic observations, such as the emitting region sizes given by Event Horizon Telescope. And we're going to be classifying the model parameter space using movies. So stationarity is something that we seek because there's a very rapid variability in the Galactic Center. So we can start to get at some of this using observing JAB simulations. And there are going to be some future horizons that we consider. Among them are the variable quasar 3C279. And we're going to be modeling this variability using simulated light curves and semianalytic models. Now, the observing JAB simulations pipeline can be described as follows. You start with a general relativistic magnetohydrodynamic simulation or semianalytic model of a jet or outflow accretion flow black hole or JAB system. Then you convert the GRMD variables to radiation prescriptions for emission, absorption, polarization, particle acceleration, and their dissipation to emulate the source properties. And finally, you add an observer in post-processing to observe, to fix ideas here, Event Horizon Telescope targets. So initially there's M87, which we focus on because we have these observations dating all the way back from the 2019 first image in the immediate vicinity of a black hole. And now we've done it also in polarized light. There's Sagittarius A star, our Galactic Center source, which is rumored to host a 4 million solar mass black hole that we haven't really imaged yet. And then there is 3C279, where that's a source that we actually have images of the jet base with the Event Horizon Telescope. But we haven't quite seen any ring with the central depression yet, but we still have multi-wavelength observations that are quite informative to cross-check across different aspects of different emission models. So first, since this may be a pretty mixed audience, let's get some terminology out of the way. And active galactic nucleus, or AGN, is an emitting region surrounding a supermassive black hole appearing as a discrete source. And accretion disk is an inflowing, typically magnetized, gravitationally bound flow to the massive object. So here's a simple view of NGC 7742. There are a number of flavors of accretion disks. So here are more acronyms. There's magnetically arrested disk, in which the disks that are inflowing can actually be arrested due to the buildup of magnetic pressure near the horizon. And these MAD simulations or MAD disks can be contrasted with standard and normal evolution, which is of course sane. So polarization is a key tool to understanding the underlying structures of these objects, and it can be parametrized by the total intensity I and these two independent linear polarizations, Q and U, and the remaining polarization being the circular polarization V. A jet is a relativistic outflow emitting from about 10% of active galactic nuclei supermassive black holes. And Blandford-Nyack jets, which you see on the cartoon at the right, are formed by the interplay of black hole spin with magnetic fields yielding Poynting flux. And synchrotron radiation is a pretty prevalent radiation mechanism for the frequencies that concern us at the Event Horizon Telescope. And you can imagine in the cartoon on the right that there would be charged particles that would be gyrating around magnetic field lines, and these accelerating charges produce this polarized dipole emission known as synchrotron radiation. And inverse Compton radiation is another radiation mechanism that may be at play, and that's radiation of scattering of particle scattering photons, thus giving up their kinetic energy to them. And the key methodology that we are going to be using is solving the radiative transfer problem for a lot of these sources. And radiative transfer in general links source properties such as the emissivity function to observed radiation. So here's a pretty simple application of the radiative transfer problem, where the source properties are included in the emissivity function J, and they could be integrated along the line of sight to give you the intensity that you observe. And that's, you're observing at a particular observing frequency. So we can call these, we can have subscripts with news on them. And the full polarized radiative transfer is actually a bit more complicated. It's a system that involves effects such as not only these emissivities for all of the polarization channels, but there are absorption coefficients for all of them as well. There are Faraday effects such as the Faraday rotation of the linear polarizations encoded in these rho V's, and there's the Faraday conversion of linear to circular polarization. So we actually have a complex 4x4 system that's coupled. So it's not always obvious when you change one of the coefficients, what's going to happen to the observed Stokes maps. So that's a problem that we address, but we can also extract some scaling relations that for synchrotron radiation, we note that these radiative transfer coefficients depend on the pressure of the relativistic emitters, which we often think of as electrons, but electrons and positrons may actually have profound effects on the Stokes maps that you see. And these coefficients also depend on the magnetic field and the observed frequency. And they also depend on the pressure of the emitters, which we can see depends on the number distribution or the particle distribution function, which can take some stylized or some simple forms such as thermal, where n of gamma, where gamma is the Lorentz factor of a particle, decays exponentially with that constant electron temperature that you see represented by theta E governing the decay. Or we can even have power law decays. And we also note that for the particular plasmas that we are discussing, they have distribution functions that are not necessarily relaxed into, say, thermal distributions. They have very long Coulomb mean-free paths, and we may actually have to resort to parametric modeling in order to really understand what's going on with the particle distribution. So in order to do that, here is where the modeling step comes in the observing GRMD simulations pipeline. And to model what's going on to set emitting particle energies, why don't we consider a turbulent heating model? So the first parametric model we consider is actually going to express the ratio of the ion to electron temperature in terms of the plasma beta. The plasma beta is the gas pressure over the magnetic pressure. And this model has the behavior of at low beta, you converge to a low constant of Ti over Te, or low. And that ratio goes to a high value at high plasma beta. Note that this is not the only way to interpolate between these two behaviors, which we're going to go into later with other emission models, but it does capture this turbulent heating model that was pioneered by Greg Howes in investigations of the solar plasma. And we can also think about slightly different physics that could be responsible for heating particles. So think about constant beta E and its implications on having the component of the beta that's due to the, say, electrons, PE over PB, be a constant value. This model scales that electron pressure to the magnetic pressure, and it says that you have a fixed amount of conversion from magnetic pressure to the pressure of the particles. And this model can represent equipartition of the particle energy and the magnetic energy if that constant beta E naught is 1. But we typically are going to be applying this to jet models where we're going to have this beta E being less than 1 or sub-equipartition. So this is a very, very simple, intuitive way of parametrizing the pressure of the relativistic emitters or the temperature. And we can also generalize this to a magnetic bias model. And in this magnetic bias setup, we actually scale the electron. Oh, go back. Yeah, in this magnetic bias model, we actually scale the electron pressure to powers of the magnetic pressure. And this model is, of course, you're going to need a normalization constant if you're going to be mapping pressure to the n. But this is motivated by knowing that the magnetic fields sometimes have simple properties or scaling relations with distance from, say, the axis of a axisymmetric rotating black hole and jet. And we can take advantage of some of these in our emission modeling. So we are now going to turn to our first application, which is M87. And this is a prototypical jet accretion black hole system with a prominent relativistic jet. And M87 is a giant elliptical galaxy that's, again, 54 million light years from us. It sources emission from radio to gamma rays. And we're going to be focusing on a few of these observations. So we have the following from 90 centimeter very large array, where you actually see the lobes of the galaxy. And then you actually can go down in wavelength to 20 centimeter very large array. And then going to very long baseline array observations there exist at 20 centimeters and also 43 gigahertz, where this 43 gigahertz is actually a one of the more frequently used in this emission modeling approach, because you actually see that it has this distinct limb brightened structure. And it also has, beyond that unresolved core, a counterjet that's visible. We also have observations at the 100 gigahertz very long baseline interferometry network. And lastly, we have the observations directly resolving the central black hole by the Event Horizon Telescope. And this direct imaging approach by the Event Horizon Telescope actually gives us a black hole measurement that resolved a long-standing dispute in the literature. So Carl Gebhardt's group at UT Austin had since 2011 about a 6.5 billion solar mass black hole by stellar dynamics. And this actually butted with some of the gas dynamical measurements that were about half of that mass or half of that length scale, since we're dealing with a black hole. And the Event Horizon Telescope actually directly sided with the stellar dynamical measurements. So there are a few discrepancies like this that Event Horizon Telescope will potentially resolve. We also note that there are polarized imaging observations, and they've also been done in many different scales and many different wavelengths. So there's 1,000 light year scale ALMA observations, where we actually see that there is some order on the level of the knots of plasma flowing out and that core. And also we see that there's even more order at the VLBA 43 gigahertz scale, where we actually see the indications of turbulence in the stripes, which are representing the polarization directions in these. And lastly, the Event Horizon Telescope scales, we see that there is order in these azimuthally spiraling electric vector polarization angle patterns. And these are actually prominent only in that southwest corner. And notice I'm speaking like an astronomer, because southwest is like the opposite of east and west that you would think of looking at a map. Because we're looking up at the sky, we're looking down at maps, I guess. So, but we do see that there's actually a very, very ordered spiraling pattern of electric vector polarization angles that we can try to infer what's going on using what we know about the mapping between electric vector polarization angles and magnetic fields. So we
has some similarity with the Sophia observation of our polarization.
Of what source? What?
I'm saying our, like for the Sagittarius A star, the Sophia A. I remember they released an image of the polarization for the magnetic field near the black hole.
Well, I think I'm going to get to what simulations favor this particular configuration. So if you see polarization in this pattern, well, I also can't say too much, but let's just say that there's a particular type of simulation that has a particular amount of magnetic flux going into black holes that produces this type of pattern. And there are other simulations that produce another type of pattern. I can't speak specifically about what the Event Horizon Telescope has done for Sagittarius A star, because that's a work in progress. But I think in the next few slides, you're going to see that there's at least some characteristic patterns that you can infer based on what your observations are showing you about the electric vector polarization pattern and what the underlying magnetic field structure is. So yeah, that's a great question. So we note that these radial electric vector polarization angle patterns correspond, if you do with your right-hand rule and you consider the light that's coming towards you, they correspond to these ring symmetric or toroidal magnetic fields. And the significance of that is that the toroidal magnetic fields just go with the flow. It's an accretion flow that's accreting, and its symmetry is mostly toroidal, and it's not the same flavor as some of these other magnetic field configurations that we're going to consider. So consider the electric vector polarization angle pattern that you would see being radial. That would actually imply being toroidal. That toroidal electric vector polarization angle pattern actually implies a radial magnetic field, and this magnetic field is very dynamically strong, and it's not just going with the flow of the plasma at all. We can think about also another case where we have these spiraling symmetric electric vector polarization patterns that are consistent with the M87 data. And in this case, you actually have vertical magnetic fields, so vertical coming in and out of the page. And this picture is actually compatible with that cartoon that we saw of that Blanford-Nyack jet of these jets that are formed by the interplay of the rotating black hole with the vertical magnetic flux. So this is actually telling us that we can use those observations to pick out some features about what the physics of the plasma is. So in order to do that—
That's how the orientation of this jet of M87 is with respect to the plane of the sun.
It's about 20 degrees. So all of the observations so far suggest that it's between 15 and 20 degrees to our line of sight. So on almost all the scales, it's like, if I'm looking at the black hole of VHD, I'm basically looking down a jet that appears to be doing this. So the projection angle from straight is like 20 degrees. Yeah. So the way that we can actually start to extract some of the parameters and learn something about these is to compare simulations with various spin and accreting magnetic fields to the observed patterns. So again, we start with that R beta prescription for assigning electron and ion temperatures, or electron simulation temperatures. And using the scan that you see on that grid, you see that there are simulations that like fixing R low to be 1. The simulations vary R high between 1, 20, 160, and they also, if you look at the top row, they vary between accretion modes of standard normal evolution and magnetically arrested disk. And also they vary the spin from extremal retrograde A equals minus 0.94 to 0 spin to A equals plus 0.94. And some of the trends that we see are that if you are in those 0 spin columns, like second column and the fifth column, you have a more symmetric image than if you have the closer to extremal spins. And this makes sense because of relativistic beaming of plasma that's moving towards the observer. We also note that the 0 spin models tend to be disfavored, and they would also be disfavored by the Blanford-Nyack picture, where you actually need a rotating magnetic field to launch a jet. So this really all hangs together so far. The polarization angle pattern, the power of the jet, and the morphology that we actually observe. We also note that the MAD simulations tend to have the mostly spiral electromolecular polarization angles with the implied vertical magnetic field, whereas the SANEs have more radial electromolecular polarization angle patterns and more toroidal implied magnetic fields. So, using these libraries, we haven't decisively narrow down the exact part of parameter space that we know the observations to be, but we actually do have a fairly coherent picture of that Blanford-Nyack jet that's rotating and stopper boosting some part of the image, and the polarization angles structures actually shed some light onto what that structure of the jet is. Now, we are going to fix ideas, and we're going to focus on a particular GRMD simulation. That simulation that I'm going to focus on is a geometrically thick disk. It's going to be a MAD simulation, magnetically arrested disk, and it's going to have the jet power derived from flux threading, fairly rapidly rotating and progradely rotating black hole. This code that's going to solve for the fluid in this simulation is going to have the mass conservation that you see by that continuity equation. It's also going to have this conservative code from Harm is going to have the stress energy momentum tensor for divergence go to 0. And the components of the stress energy momentum tensor are going to include contributions from the rest mass density rho, the total gas density UG, not just the electron part of it, the total gas pressure PG, which is linked to UG by an equation of state, the magnetic pressure, and if you now analyze the cross section of it, you will see that there is this dense or orangish equatorial inflow. There is an underdense outflow, and the underdense outflow has this very clear coherent magnetic field structure indicated by the arrows on these scales, where the gravitational radius RG, or sometimes called M, is half of a Schwarzschild radius. So in what follows, we're going to be using that simulation with some power law coefficients in radiative transfer to see if we can model the behavior of relativistic jets. So the modeling step actually first involves constructing this synchrotron emissivity function that's in this mostly optically thin regime. We're going to just envision setting the electron pressure or electron plus positron pressure, but just to focus for the simplest models here, the electron pressure is going to be given according to the magnetic bias model or constant beta E model, where this PE is going to be a power, it's going to be a power of the magnetic pressure. And judging by the distribution of the magnetic field strength and magnetic fields in this image, we can sort of intuit what a bias model will start to do with jet collimation. So we note that there's a parabolic jet collimation profile where these are cylindrical coordinates S and Z. And if we start with the n equals 0 bias model on this panel that you see at the left, the bias model eventually scales the emissivity as b to the 1.5. And we see that there's a fairly broad collimation profile. There's going to be some isolation of the jet region that we're just restricting these types of models to. We don't want to model an accretion disk with a completely different plasma with the particular painting that I gave here. But this is just to show that if you increase that n parameter in these bias models, then you get what you might expect is a much more collimated profile. And these are just very, very simple toric models that are letting you see how the magnetic field strength scaling can be intuited and tied to a particular parameter that governs this. And this is work that I've done starting at Berkeley with Jeremy Whelan when he was an undergrad. He's now a PhD student at Chapman University. Now we can also think about some more phenomenologically motivated and some more intricate models. And the models that we are going to be describing for the M87 jet, I want you to envision as being painted by having the pressure due to the relativistic emitters go like some dissipation rate per unit volume per unit time W, and the time scale that's given by some minimum cooling time from the radiative and expansion cooling times. And in this model, we can actually directly input in this W parameter where we formulate prescriptions that are based on mechanisms of particle acceleration that we might think of as current density J, shear stress tau, or shear strain S, so that relativistic object there, where strain is dVz ds, where S is a cylindrical radius and Z is altitude. So if we use these types of recipes to make our emission models, we can actually start to phenomenologically assign what the pressures would be in each of these cases. So one model that we can consider is a model that's motivated by Shakura and Sunayev's alpha disk. And that alpha disk has some sort of parameter governing the efficiency which angular momentum can be transported in a disk, because in order to have the material flow back on the disk, you need to get angular momentum kicked out. And now let's think about a jet alpha model where we actually have tau being parameterized by alpha, which is thought of as the efficiency of linear momentum transport. And we can actually visualize a model like this. And we can also change the prescription to make it a model that's based on Newtonian shear. So shear that's mediated with this dynamic viscosity. And that model is roughly edge brightened compared to the alpha model. And this model is governed by a parameter shear strain S, which in the end, with multiplying by tau S in the pressure of the emitters, gives us a model that goes quadratically in the shear strain. And we see that this model is brightened in some shear layers.
So one question, this is all done in post-processing, right?
Yes, yes.
Is it a good assumption that when you change these parameters, you shouldn't expect the dynamics to be changed?
Yeah, so there are some simulations like the Coral simulation that try to start to get out the effects of radiation in general, relativistic radiative magnetohydrodynamics. And at this stage, if we're just changing a small percentage of the particles that are contributing to emission at the observed frequency, dynamically, they're not going to be that important. But to do it more self-consistently, we can do 2 fluid or more simulations. And those tend to be a lot more expensive than the post-processing here. So I'm going to be showing a lot more models. And it's just computationally, it's not feasible to really change every single thing about the underlying GRMD fluids. But yeah, it should be done more self-consistently should we get the opportunity.
And another question is, so for example, here you see some enhancement on the size or things like that when you change this parameter. Could this be accomplished by having the dynamics be different, but the radiative transfer stuff also? Can you change both things at the same time and get back to where you started in some sense?
Oh, there's tons of degeneracies in these models. I think that the main thing to try to see with this illustration with phenomenological models, we're going to start just mapping, parameters that you can intuit into features and seeing if those discrete features are very, very highly responsive or very clear signal based on some of these models. That's just the basic takeaway that I want from these. This isn't supposed to be a perfect rendering right now or non-degenerate rendering, but it's really to start doing a lot more probing of emission physics than can currently be done by just making some of the canonical assumptions that are being done currently in the literature. All right, so another exercise we can do is we can input in a pressure due to emitters that goes like the current density squared, which current density in jet, you can usually envision as the curl of the magnetic field in these force-free situations. And I could ask, guess which one's the model on the left or right. Of course, I labeled model on the left, and it's kind of, for people who've been looking at VLBI images, it's kind of obvious that the model is going to be on the left. But here's what happens when you actually input in this current density prescription. So you know that there's this like spine of outgoing current, but then you actually see splaying current sheets. That's you can even think of the system as a coaxial cable type of system where there's a mostly outgoing current, and then there's a thin layer where all that return current is coming in. And those types of features are reminiscent on the observations that you see at the right, where you actually do see some limb-brightened structures that appear to be roughly flailing around this. So of course, there are some issues with relativistic beaming of some parts and how to make the interior of the spine less prominent, but this is just an illustration of how you can get some of the mapping between some things that you can come up with a phenomenological model that is quite simply explained as a coaxial cable model, and you can explain some of the features like limb brightening. Of course, limb brightening is more complicated than that and probably comes at further from the jet in terms of ionic plasma in shocking these boundaries. But it's good to be able to start to isolate some of the phenomenology by observing these JAP simulations. So having observed some of these simulations, the next step that we do is to abstract out that simulation and turn it into a semianalytic model that's based on a few simplifying assumptions. So assume stationarity, axisymmetry, assume a self-similar paraboloidal jet with a self-similarity parameter C, as we might use later on. And we can use this force-free assumption to use electromagnetic theory in order to get us what the simulation profile should look like in some of the fluid variables. So we have in this, the smallest scales, we see that there is a parabolic vertical field profile that is given by the arrows. There is a toroidal magnetic field that's strongest in the colors in the intermediate cylindrical radii. The jet keeps collimating on larger scales, but it doesn't really focus. And we see that the structure becomes roughly vertical on the larger scales. So we can use the semianalytic model in order to observe and see if we can deduce further consequences. And one exercise that we can do is we can put in that constant beta E model to the semianalytic model, and we can observe intensity with electric hyperpolarization angle patterns on these. And some things that we can start to see are that we can actually extract out the magnetic field dependence into this B effective, which depends on that Doppler factor that gives you some of the relativistic effects, and also depends on the magnetic field only as the combination B cross N hat, where N hat's the observer direction, which is roughly constant on that intensity map. And what you can see through this is that if you have a magnetic field structure that is roughly toroidal and changing pitch angle as the jet goes out, then B cross N hat will be different on the two sides of the jet. So you can actually start to explain the bilateral asymmetry in the semianalytic model. And you can explain more of the limb-Brighton polarization angle pattern by observing this model with polarization. And you see that's a core of polarization with roughly limb-Brighton polarization angle pattern. And this starts to approximate some of the features that you see in the observation at 43 gigahertz on the right. We can also, in the semianalytic model, add positrons, and positron effects are potentially important in the polarized emission that you see from some of these sources, even in the unpolarized emission, but especially in the polarized emission. So why would positrons be even in these systems? There are a bunch of interactions that can produce positrons in active galactic nuclei. So first, let's consider the Bright-Wheeler pair production that occurs due to photon-photon collisions and photon-photon collisions in the funnel specifically. So you can imagine photons originating from different parts of the AGN, colliding with the funnel of the jet, and creating these soft, so basically having soft photons scattering to MeV energies that end up in these photon-photon collisions that produce pairs of particles. And this type of interaction can occur in jet funnel walls. And in fact, this has been modeled in some simulations to produce, depending on the specifics of the AGN, either very few or a significant amount of pairs. So the simulations for Sagittarius A star give you photon content that's much less than the Goldreich-Julian density of positron content that's much less than the Goldreich-Julian amount that would be required to screen electric fields. But in the M87 case, you actually get a substantial amount of positrons being created. That AGN is much larger, and the magnetic fields and potentials actually give you enough positrons that you couldn't make a substantial difference in the modeling. We can also consider spark gap processes. Spark gap processes are, as depicted in the cartoon on the right, you can have a region between accreting plasma that's going down and outflowing plasma that's going up in a jet. And the low density regions may end up being roughly unscreened. And here's where Goldreich-Julian values of density actually start to matter, where if you don't have enough density of charges to start screening these electric fields, you can have these spark gaps. the spark gaps can end up accelerating particles into cascades. These cascades can end up producing synchrotron radiation that we may be able to see. So with these pairs, we can actually start to see why we might need to put them into our formalism. And it's easiest to put them into the Semianalytic models. So we can actually do that by starting to generalize radiative transfer coefficients. In particular, assuming charge neutrality locally, we can have positron number density in addition to the ion and electron number densities. And now we have modified radiative transfer coefficients. So with these modified emissivity and absorption coefficients and Faraday coefficients with different relations with how they're affected by the positron fraction, we're going to see some of the effects in this coupled system. So putting in a constant electron beta model with some of this positron model, we can actually see that's on the Stokes maps I, Q, U, and V on the top that have no positrons, and the ones on the bottom, at the level of total intensity, we don't really see much of a difference if we normalize the total flux to be the same. However, if we look on the second and third panels with the linear polarizations, we first can notice, if you can see the scales, that there's a lower degree of linear polarization or lower linearly polarized fraction of this emission that's being emitted in the no positron case, as there is, as we might expect in the higher positron case, because the positrons are going to be adding some of this linear polarization. They also do change the polarization angle patterns and the order of the fields in a way that depends on the model parameter beta E, which actually couples some of the radiative transfer coefficients. And there's also circularly polarized patterns that also are affected by the positron fraction. We can move it to a slightly different part of the parameter space with adding, or increasing beta E naught. And we see that increasing beta E naught, what it does to the total intensities, is it somewhat symmetrizes the ring of emission that you see, but you still don't see much difference between polarized and, between positrons and no positrons. However, with the positron fraction, again, you see there's more linearly polarized flux in the high positron case for the same type of total intensity image. And there's also, this time, there's more order in the linearly polarized patterns in the high positron case. And also the degree of circular polarization does change, and it changes in a way that's a competition between intrinsic circular polarization and the Faraday-induced circular polarization, as we're going to see in the spectra. So we can also decompose the polarized the spectra into their polarization components, and comparing with some data, we see that the I spectrum, when we change around both the positron fraction F positron and the power law index P, we see that the spectrum is basically totally degenerate in low frequencies, like less than 10 to 12 hertz. But the spectrum actually breaks according to what optically thin synchrotron would predict, basically just in terms of the power law index. So we can find the power law index that best matches the data. And also, if we look at the linearly polarized spectra, there's a different story at the low frequencies. The low frequency spectra are now non-degenerate, both in the power law index and the positron fraction. In the circularly polarized case, the entire spectrum becomes non-degenerate, but these are the hardest observations to make. However, there is now a very distinct signal of maximum positron fraction. So we can actually start to look at all those long dashed lines have a very different decaying behavior at the high frequencies than those dot dashed and the dotted lines with lower positron fraction. And this is because in that the long dashed line with the maximum amount of positrons, they completely cancel the intrinsic circular polarization. And the only thing that resurrects any circular polarization are the Faraday effects. And these Faraday effects are minimal for the highest positron case, and they actually are more important in the lower positron cases. So this is actually a probe that could actually be a clear signal that distinguishes a positron rich versus a positron poor jet, as long as we have that data. Now, we can also put some of this post-processed positron modeling into GRMD simulations that are fully 3D. And we can do that by considering an increasing positron, increasing fraction of pairs of electrons and positrons being added to some original number density of electrons. So in the case of this magnetically arrested disk simulation, note how the circular polarization angle degree, V over I, changes as we add these pairs. So no pairs all the way up to a number of pairs that's equal to the original plasma content. That circular polarization angle, circular polarization degree goes down by, it basically goes down by 2/3 of its original value. So it ends up as 1/3 of its original value. And start to think about how that makes sense intrinsically. So if you are adding positrons that are paired with electrons, each one of them, if you imagine them gyrating around the magnetic field line, the electron will do something, the positron will do the other thing. And the circular polarization would cancel if it's just intrinsic circular polarization. And this is what happens when you add it so that 2/3 of the emitters end up being paired. So now you get 1/3 of that intrinsic circular polarization on the movie on the left. But on the movie on the right, something very different happens. So now you have the electron vector polarization angles rotating very rapidly, and you have this pixelized spatially varying V over I pattern, but the circular polarization angle degree doesn't just decay down to 1/3 of its original value. And this is because the Faraday effects are a lot more prominent in the sane or standard normal evolution. These don't rely on the magnetic field strengths to create that intensity. So the densities are a lot greater in these to normalize to the same image flux. And when we do that, we notice that the positron effects are felt more distinctly in the electrovector polarization angle pattern. So let's play the MAD movie again. You see the EVPAs or these stripes, green stripes are not moving. However, the Faraday depth of the sane has such a large value compared to the MADs, like 1,000 times more, that a small fractional change that's of a positron fraction causes a small fractional change in that Faraday depth. And that Faraday depth is proportional to the amount the electric vector polarization angles will swing. So here could be another way to disfavor, say, sane simulations if we don't observe that type of electric vector polarization angle behavior because of the differences in the Faraday effects that you can start seeing by if you observe a changing positron fraction. And this could also confound things like using axions in order to see if their electric vector polarization angle patterns are affecting if the positron content, sorry, if the axion content would actually affect the electric vector polarization angle pattern by inducing an oscillation. So this is another systematic that wasn't usually included in the model. So I'm gonna go, maybe I'll even take a vote. So there are two applications coming up, Sagittarius A star through C279. I probably have time for like half of one of them. So anyone have an opinion on Sagittarius A star or 3279? You want Sagittarius A star? All right, we'll do it. See, that's what happens when you volunteer first. So Sagittarius A star, I have actually another movie. So Sagittarius A star is the source at our Galactic Center. And we note that our Milky Way Galaxy in this movie, what should be a movie. Right, yeah. So we have a Milky Way Galaxy that is about 100 kiloparsec or 300 kilolight year in diameter. It has a dark matter halo, and it also has about 100 to 400 billion stars. And this Milky Way also houses our planet. In fact, it houses the IAS, it houses all of us. So we're passing us right now. We can't see it at this resolution, but it's our Earth is about 8 kiloparsecs from the Galactic Center. The Galactic Center, at least on the parsec scales, have very eccentric stellar orbits, which we're going to see when this stops pulsing around. So we should be seeing these eccentric stellar orbits. This movie actually stopped. No, yeah, there we go. So at the central parsec, we see these eccentric stellar orbits that are surrounding what has been inferred by a number of observations to be 4 million solar mass black hole. But we also have observations in infrared about bright spots of emission. And our question is, what happens here? So that hasn't been resolved yet. So Sagittarius A star at a glance, we already really zoomed in. It is the source between the constellation Sagittarius and Scorpius. It is it has a non-thermal emitting region, and it also has a region that's the brightest that is surrounding the black hole at 8.18 kiloparsecs from us. And we actually know that distance to 1% because of the work by gravity. We also know the black hole mass to about 1% because of the work by the gravity collaboration. And Sagittarius A star has a very mysterious low luminosity accretion flow. So like think about 10 to the -9 times the Eddington ratio, which is very small. And it's modeled well by a radiatively inefficient accretion flow. And the mass accretion rate is also quite small, of 2 times 10 to the -7 solar masses per year. And the observations that we have are, there are emitting region size constraints that were given by the Event Horizon Telescope by measuring the flux density versus baseline length. So that can start if we have a model, let's say a really simple model of a spherical Gaussian distribution of intensity, that would correspond to visibility versus baseline going like this. But in reality, it's more complicated. It's actually a ring, or it's more likely a ring. It's more likely to have some non-point symmetric type of emission profile with way more complicated visibility amplitude per baseline. So we can model it really simply as a spherical Gaussian with a 37 microarc second characteristic size or full with half max, or we can model image moments to really think that this is anisotropic distribution with a 56 microarc second anisotropic size. We know that the spectrum is supported roughly from 10 to the 10 or 10 gigahertz microwaves down to 10 to the 20 hertz X-rays. There's a sub-millimeter bump in the infrared, and the observations can have the flux at 230 gigahertz be constrained to be around 2.4 Jansky, which we use to normalize some of the images that we're going to produce.
Can I ask a question about this? Flux of Sagittarius has not been 2.4 Jansky since like 2000 something. It's been average at 3.5 Jansky since the last at least 10 years. Why the simulation still assume 2.4?
Well, 20 years. It depends on how close you're zooming in. I mean, if you're getting like, you could have a larger region corresponding for flux.
But I understand that, but wasn't that we know that most of the emission is coming from inner field torsion radii. I'm not saying that you zoom on the whole galactic center and combine it. I'm saying that you do as close to the galactic center, and you going to be at 3.5 for the last at least 10 years.
Yeah, I think it. My guess is that it still depends on how much of that flux you're getting in your field of view. But if you're talking about a very specific field of view, then we can probably narrow it down more closely. So maybe like what size exactly you're talking about?
Point source of the location of Sagittarius star smaller than 0.01 arc second.
Well, yeah, I mean, it could very well be their updated measurements, but there's some. It could very well be that they're just trying to be consistent with previous work that's in the literature, because if you have these images normalized to different amounts of flux, then you're not going to have an apples to apples comparison. But then again, there could be issues with like differences in what specific measurements they're looking at. I mentioned field of view. There might be other, scattering models. There might be other things that are contributing flux or not contributing flux. What beam you're using. So I'm not an observer myself, so I'll take your word for it. But there could be a couple of classes of explanations having to do with either the specifics of the observations that's being used or consistency with other things in the literature. So we are going to be modeling this Sagittarius A star with the a simulation that I call a semi-mad simulation, which has intermediate time average magnetic flux between magnetically arrested disk and standard and normal evolution. So we are going to note that the dynamical time for collisions between the electrons and positrons is a lot slower than, between electrons and positrons versus protons is a lot slower than the time it takes for accretion to happen. So we have a 2-temperature model. And we also note that electrons radiate their heat faster than protons due to the way synchrotron emission works. And this simulation is, it actually has contributions from a stress energy momentum tensor that includes viscosity and heating. The simulation actually evolves out the electron fluid differently from the proton fluid, and the electron thermodynamics are constrained by actually using the Vlasov equation and its moments to get an entropy. This electron entropy governs the electron evolution and the electron temperature. With this electron evolution or non-parametric model, we also note that the simulation looks like a lot like the M87 simulation in terms of where it's less or more dense, so it's least dense at the equatorial outflow, but the electron temperatures tend to be highest in that outflow. So having that picture of that simulation in mind, we can start our emission modeling. So in this Sagittarius A star parametric model, we also hark back to the turbulent heating behavior, only now we have a different parametrization. In this parametrization, the electron to total temperature depends on its overall parameter F, and it also is exponential in the plasma beta. So now that even though it goes to constant at the low values of beta, it's exponentially suppressed at high beta. So exponentially suppressing the electron temperature will give you different emission maps. We also recycle our old emission maps, our old emission prescriptions from before of the constant beta E prescription, which is equal partition or sub-equal partition, and that magnetic bias model. And we can now look at the behavior of the electron temperature profiles on vertical slices in these two classes of models. So that the critical beta model parameters scan with that exponentially decaying electron temperature governed by that beta crit exponential parameter. That model actually across a parameter space where you have the F going from 0.1 on the top to 0.5 on the bottom, and beta crit going from 0.01 on the left to 0.1 on the middle and 1 on the right. It actually has the same behavior in that there's this interface layer of a disk jet corona that's always the brightest in this entire parameter scan. So it's like this interface is always the highest electron temperature. Now we know that there's a different type of behavior in the electron temperature in the equal partition inspired models. So those constant beta E and those bias models, they all have the spine having the highest electron temperatures. So we put these into post-processing to find images. And one way we get images is through the ray tracer called Ibothros, which includes synchrotron emission and absorption. And it ray traces images like that non-parametric electron evolution framework that we saw for the simulation. So here's an Ibothros image where we see that there's a lens profile of inner disk emission with some hints of the outflow. We also can post-process spectra. The tool that we use is GRMD. GRMD includes synchrotron emission absorption and Compton scattering, and it can give us spectra compared to the data. Here's a snapshot spectrum at the time that's equivalent to 10,000 gravitational radius light crossing times, where gravitational radius light crossing for Sagittarius A star is 20 seconds. Now we can compare our models in this parameter space. So that vast parameter space that I talked about can have these the critical beta models on the left and start focusing on them, where we saw that the behavior of the electron temperature being highest in that disk jet corona, that actually translates into images that appear as these projected coronal regions. But when you actually increase the F and beta crit parameter, you get increasingly compacted asymmetric images that tend to be more concordant with the size constraints. So the green size constraints are the ones that pass that EHT size constraint that I described earlier, the one that was at least circularized, or the isotropic size constraint. We can also do the same exercise with the constant beta E model. So if we look on that on the right in the middle row, we have beta E equals 1, and you see that thick torus of lens disk emission going down to beta E naught equals 0.01. This, again, thin, compact, asymmetric crescent, which is actually somewhat degenerate with the highest F and beta crit models. We can also start looking at the torus from the n equals 2 magnetic bias models, and then go down in the bias model parameter to n equals 0 as we go on the right up. And when we do that, we actually see that we have this outflow dominated emission profile that's roughly conical. So we have a number of degeneracies here that are at the level of that isotropic size constraint. We can also consider the anisotropic size constraint, and we consider that not just with our fiducial simulation, but with not sane and mad simulations. And the trends that I basically want to extract are with the anisotropic size constraint, that's the theta max, or the larger semi-axis, tends to go down with increasing F and beta crit in the critical beta model. They tend to that size tends to go up with increasing constant beta E, and it tends to go down with increasing bias model parameters. And the key upshot is that it's still the highest F and beta crit model, but now it's more exclusively the highest F and beta crit model rather than the other types of models that were degenerate with it that are producing the best sizes. And this is work that I actually have done, or I'm continuing to do with Elon Price, who was a Fitz Vanderbilt master's student. She recently graduated on our EHT program scholarship that actually started at the Smithsonian Astronomical Observatory. And doing that project, she's now studying plasma physics as a PhD student in Auburn. So now that we've classified, so now that we've delineated our model parameter space, I'm going to spend 5 minutes talking about the trends with the variability. So Sagittarius A stars, the dynamical times of minutes as opposed to days, have thus far precluded its direct submillimeter reconstruction. However, we can note that that model parameter space that I showed above has a few characteristic morphologies, and they basically boil down to those 4 types. So type 1 is a thin, compact, asymmetric photon ringer crescent. And note that type 1 actually comes in 2 varieties because of the spectrum can either look a little bit like the data, or it could be flatter than the data. I'll show you some examples of flat spectra later. Type 2, you have these coronal projections that appear to be these inflow-outflow boundaries with a thin ring in the center. And these models have these bright spots that move quite a bit around the profile. These models have steeper than observed spectrum. So you can think of like a rapidly expanding coronal region where the temperature increases or decreases rapidly in radius, producing this very steep spectrum. You also have flatter spectra. So these flat spectra that are in the type 1b or this other type of morphology, type 3, have this thick crescents of lens discommission, where the bright spot just makes these like pulsing but not very large excursions, just like pinch the equatorial plane. And then there are type 4 models where we have this morphology of this extended conical outflow and the flat spectrum. You can think of this as a Blandford-Konigal type of model of emission, which I would have gone over with the thesis design, but for the interest of time, we'll just leave it at that. These models tend to have the pattern of being envelopes of roughly fixed emission with bright spots that may or may not move around them. And this is important when we consider there's models that are concordant with the imaging spectral observations, but with the variability, we'll see that the greatest variability comes from the ones that have the most excursions around the envelope of the bright spots. So the variability can be broken down into light curves of millimeter emission. So we have the type 1 models that you see, those like thin crescent shaped images, also having the greatest variability, and this is most concordant with the observations. The type 2 models, or those projections of that coronal region, have also have significant variability. But type 3 models, the ones with those bright spots pinned to the equatorial plane, they are very featureless. So they're actually completely precluded by completely lacking minute scale variability. And we also have type 4 models with thin outflows that are also not very variable. So we can actually start to pin down a story that tends to favor these type 1 models on the grounds of their morphology, their spectra, and their variability. And lastly, I want to compare the Event Horizon Telescope with gravity. The gravity collaboration observed the Galactic Center at infrared frequency slightly higher than the 230 gigahertz we're looking at. So if we have models that have the EHT frequencies or 230 gigahertz on the left versus 140 terahertz on the right, and we change the inclination angle, we can actually see hints in the upper right corner of these infrared bright spots that the gravity collaboration saw. So I am not going to go over this future direction of DC279, but I am going to leave you with my conclusions and questions.
Thank you very much.